Welcome to another coding tutorial, and in today's video I'm going to show you how to make the double pendulum fractal. I recently did a tutorial on the double pendulum, and while doing some research I came across a bunch of videos with the name the double pendulum fractals that create these super cool visualizations. So I dug a little bit deeper to see how it worked, and in this tutorial I'm going to show you exactly how to do that. If you enjoyed this video, I also recommend that you check out my tutorial on flow fields that uses a similar technique of creating a grid of vectors as a base for the visualization. Alright, before we get started, let me walk you through what is a double pendulum and how to simulate its movement. A double pendulum is a set of two pendulums, one hanging off of the other, and it is a prime example of a chaotic system. A chaotic system is a system that is super sensitive to initial conditions, meaning that slight differences in how you start the systems can result in drastically different movements. To calculate the motion of a double pendulum, we're going to be using a method called Lagrangian mechanics that focuses on energy as opposed to the force-based approach that we're used to using to calculate the motion of a single pendulum. And the reason is because a double pendulum is a lot more complex than a single pendulum. Using a force-based approach requires us to take into account all of the forces acting on each of the pendulum, as well as the interactions between the two pendulums. And that is actually quite complicated, and using Lagrangian method will make our life so much easier, and so that's exactly what we're gonna do. I'm not gonna go into the details of Lagrangian method in this video, but I'll link any interesting articles down below in case you want to learn a little bit more about how it works. But basically we're gonna be using these two equations to calculate the angular accelerations of the two pendulums. Then we'll use it to update the angular velocities, which then will be used to update the angles to create the movement of the double pendulums. Don't worry if this sounds a little bit confusing, I'll walk you through each step as we code. Alright, we're going to start by creating one double pendulum, and how we calculate the angular accelerations, the angular velocities, and the angles of the two pendulums will be exactly the same as how I did in my previous tutorial. But how we display the double pendulum will be different. So instead of displaying it as the two pendulums connecting, one hanging off of each other, what we're going to do is that we're going to be actually calculating the new x and y position based on the angles of the two pendulums. And specifically, angle 1, which is the angle of the first pendulum, will determine the x value, and angle 2, which is the angle of the second pendulum, will determine the y value of the position. So let me show you how to do that. We're going to start by creating two variables, cx and cy, which I'm going to set as width divided by 2 and height divided by 2. And this is going to be the point in the middle of the canvas that connects to the new x and y coordinate that we're about to calculate. Then next, I'm going to declare two more variables, angle 1 and angle 2. And then inside setup, I'm going to set the angle 1 to be equals to, how about pi, and then angle 2 to be pi divided by 3. And these are just random values. We're going to be using trigonometry to calculate the new x and y coordinate. So let x to be equals to r, which is the radius, times cosine of angle 1, and then y to be equals to r times sine of angle 2. Alright, and then how about we use a function called line to connect the 2 points, which is cx and cy and x and y. Cx, cy, x and y. Ooh, and then I also need to, how about we set radius to 100? Alright, does this look incorrect? And you'll be right if you say yes, and that is because I missed adding cx and cy to the new x and y point. Alright, now how about we also draw an ellipse at the new location x and y. Let's give it a size of 10, and I'm going to also fill it with the color black. And then let's put stroke to black as well. Alright, so it's not moving, right? Because we have not updated angle 1 or angle 2. So how about I actually map angle 1 to my mouse location, my mouse x location between 0 and width, and then we're going to map it between the angle of 0 and 2 pi, just to give you a sense of how it manipulates this value right here. And I'm going to actually set angle 2 to 0. All right, and as I move my mouse, you can see that it changes the x value, right? And y is set to 0. All right, and how about if I were to change this to angle 2? Now you can see, oh, and then how about we set angle 1 to 0? And then now you can see that my mouse location impacts the y coordinate, right? And how about we do angle 1 is mapped to mouse x, and then let's do angle 2, map it to mouse y. So this is essentially what is going to happen. It's going to be quite chaotic changes of the x and y coordinate. That is going to be based on the equations that we're going to provide based on the Lagrangian method, right? Let me just quickly show you how we're going to be updating the angles, and then the angle velocities, and then the angle acceleration. So if I do angle 1 and increment it by 0.1, and then angle 2 also increment it by 0.1. All right, because angle 1 and angle 2 are being incremented with the same constant value of 0.1, it's basically just drawing this parameter of a circle, right? What if I change the increment to be smaller here? Then now it's a little bit more chaotic, but basically it's still changing at the same speed, right? So for each angle, and these are the angle velocity. So what we want to do actually is we want to update this by angle v1 and angle v2, and then we also want to update the angular velocity by the angular acceleration, right, for both pendulums. And then now what we need to do is that we need to calculate what angle A1 is going to be and what angle A2 is going to be. But before we copy and paste those equations, let us, how about declare all of these values first. So let's do angle V1, let's start it at 0. Angle V2 to 0 as well. Angle A1 set at 0, and angle A2 also set at 0. So for the equations to calculate the angle accelerations, we need a few more variables. So what we need is, we need the mass, let's call it m1. I'm going to set it to 1, and m2 is also going to be 1. And then we also need the length of each pendulum. So length 1 and length 2, which I'm actually going to set it to be equal to r for both. So length 2 will also be r. And then we also need gravity, which in the real world, it's 9.8 meter per second squared. But in the computer world, we can set it to whatever we want. And I'm going to set it to be equal to 1. All right. And all right, so let's copy and paste the equations. It is super long. Let's try to click run and make sure that this works. And it's not moving, and that is because the initial conditions are 0 for angle 1 and angle 2. So let's give it a little bit of value. So let's do pi over 4, and how about pi over 8? All right, it's moving quite a bit chaotically. Nice. All right, so how about now? What we can do is, now we already display it as basically an arrow, right? But now I want to map the values to a color. So essentially what we're doing with colors is that we're basically are going to be getting new angle 1 and angle 2 values every time the draw loop is run, right? And we just want to map that to a specific color. And what I'm going to do is that I'm going to actually use the sign function to get some interesting colors. So let's declare a variable called C1, and I'm actually going to set it to sine of angle 1. And sine of angle 1 will output a value between -1 and 1, right? Because that's how a sine function works. And so I'm actually going to map this value between -1 and 1 and map it to 0 to 255, which is the range of the RGB value. And then how about we just fill it with C1, and we're going to draw a rectangle at CX and CY with the width and the height of width and height. All right, so we also need to change the rec mode to center to make sure that it's not all the way to the right like this. All right, we probably want to put this before the arrow so we can actually see the arrows. All right, so as you can see, the color changes continuously based on basically how the angle 1 changes, right? So how about we do one more, and then let's call it C2. How about this time we map it to angle 2, and then let's do C2, and how about I give it the third value as 255. All right, so now we just get a little bit of this blue, purple color. Before we move forward, I actually want to show you how we can slow things down a little bit on the sketch. So as you can see, it was moving really fast, both the colors and the arrow directions, right? We can do that by actually just changing a little bit in the equations here. So as you can see here, both this equation and this equation, we're basically updating the angle with the angle velocity, and we're updating the angle velocity with the angle acceleration. But if you actually look a little bit closer, angle velocity actually has a different unit compared to angle. Angle has a unit of degrees or radians, but angle velocity has a unit of degrees or radians per unit of time. So how can we actually add them together? And we can do that because there's an assumption that actually angle velocity is being multiplied by a unit of time of 1, basically. So the assumption is that it is being multiplied by dt, or the change in time, of a value of 1, and anything that is multiplied by 1 is equals to that value, right? And so by assuming that dt is equals to 1, then angle velocity times dt now has a unit of radians or degrees, which is the same as angle, and so that's why we can add them together. But to slow things down, we basically want to change this value of dt, and we want to do it for all of these, right? So for acceleration here, the unit is angle acceleration is radians per unit of time square. So by multiplying by dt, now it becomes a unit of radians per a unit of time, which is the same thing as the unit for angle velocity. And now that we explicitly multiply it by dt, then we can set dt to a specific value. So if we just set it to 1, it would be the same as before, right? Nothing changes. But to slow things down, we can actually change the dt value to, let's say, 0.1, and now things are moving a little bit slower. So you can play around with these values as well. I'm just giving you an option. Now how about we put all of this inside a class called Pendulum. So let's come to this arrow here, click the plus sign, and then click create file. I'm going to name my file pendulum.js. And then let's go and reference the file. Go to index.html, come to this line of code here, copy and paste, change the name here to the name of your new JavaScript file, and in my case it's pendulum.js, and that's how you reference the new JavaScript file. So now we're ready to write a class. Let's call it Pendulum, and then inside the constructor function, what we're going to do is we're going to come to sketch again, and we're basically going to put all of these values inside the constructor function. Actually, I'm going to keep g and dt as global and also radius. So we need all of this, and also CX and CY, but we'll come back for that. So angle 1, angle 2, angle V1, angle V2, angle A1, angle A2, M1, M2, all right, and then length 1 and length 2. And then I actually, oh, and then CX, which I'm going to set as a parameter here, and CY. And also, we need this dot, right? For all of these, all right, this dot. And I'm also going to set angle 1 and angle 2 as the parameters as well, and also length 1 and length 2. All right, so CX, CY, angle 1, angle 2, and then length 1 and length 2. And then now we're gonna write update, and then two other methods will be called display, how about display arrow, and display color. All right, let's go back. I can delete this, G will be here, okay. And then we don't need any of this, right? All right, so this is for the update function. All right, and let's come here. All right, and we need to put this dot on all of them.
A few moments later.
One thing that I didn't do, which I did in the previous tutorial, is that we also want to constrain the value of the angular velocity. So we actually want to do it before we call this, which I didn't do in my previous tutorial. So I did it after, but because it's in a loop, I think it's okay, but let's do it correctly this time. So what we want to do is that this dot angle V1 is equals to constrain, and we want to constrain this, right? This dot angle V1 between what? We want to do it between negative max velocity and positive max velocity. And we're going to do the same thing for angle V2 as well. And then I'm going to create max velocity as a global variable. Let's set it to 5. Actually, I want to put this down here. All right, and then now we want to put this inside the two methods here, display arrow, and then display color. Perfect. All right, and we need to make sure we put in this dot, right? So this dot, this dot, this dot, this dot, this dot, this dot. Same for these. All right, so now let's create this one double pendulum. How about we call it pendulum? And pendulum will be a new pendulum object. And we need what? Let's do CX, right? CX is width divided by 2. CY is height divided by 2. And then what else do we need? Angle 1, angle 2, length 1, and length 2. All right, so angle 1 will be, let's do pi. Angle 2 will be pi divided by 3. Then let's do CX, CY, angle 1, angle 2. And then for length, we're just going to put R, right? R and R. And then let's just do pendulum dot update. So I'm going to run it just to make sure no errors. Okay, great. And then we're gonna display, how about we display arrow first? Display arrow. Great. And then let's also display color. All right, nice. All right, so now let's create a grid of double pendulums. Let's change this to an array. Then let's create a few more variables: columns, rows, and size. I'm going to set size to be, let's start with 20. And then in size setup, we need to first calculate columns and rows. So cols will be equals to width divided by size, and then rows will be equals to height divided by size. And then we're going to use a nested for loop to create a 2D array called pendulums. So let I equals to 0, I less than columns, I plus plus, or let j equals to 0, j less than rows, and then j plus plus. Inside this outer loop here, we're gonna set pendulums of I to a bunch of empty 1D arrays, and then inside the inner loop, we're gonna set pendulums of I and j to be equals to new pendulum object. So I'm actually going to copy and paste this because why not? All right. So R here is actually going to go because it's now going to be size. How about we set it to size? And then Cx and Cy will not be width divided by 2 and height divided by 2, right? It's going to be I times size and j times size. And I'm going to keep angle 1 and angle 2 as constant like this, and we can change, and we will need to change afterwards. So let's do that, and I'm going to copy this nested for loop here so that we can call these 3 methods. All right, so it's pendulums of I and j, right? All right, the moment of truth. Run. Whoa, R. Oh, we want this to be size. Actually, we're gonna do this dot length 1 and this dot length 2, which is set to R, right? Okay, let's try it. Whoa. Oh, not width and height here. Has to be size and size. All right, what do you notice here? It's a little bit off by actually size divided by 2. So what we want is, how about we put size divided by 2 here, size divided by 2 here. Great. Okay, that ellipses are quite big. So how about let's change it to be smaller. Let's do 1. And because all of them are moving together, it's quite boring, right? And that's not what we want. And it happens because why? Because we set angle 1 and angle 2 to be equals to pi and pi over 3 constant values. So we can change this. And I actually want to map it based on where it is on the grid. So for angle 1, how about we map I, the value of I, between 0 and columns. And let's do negative pi and pi. For angle 2, let's map the value of j between 0 and rows, between the value of negative pi and pi. And I'm actually going to comment out update so that it doesn't move, just to give you a sense of what it looks like. And this is another area where you can actually play around with the values, the starting values. What if we do 0 to 2 pi? The starting value would look different, right? All right, but actually, I want to start at negative pi and pi for both of these. And then how about let's first also comment out colors. Let's just look at the arrows and yeah, let's run. All right. As you can see that it is more chaotic around the sides compared to the middle, but then it's just like kind of moving in. If we make this smaller, let's do 4, you can see that more drastically. Look at that. Wow. Okay, and if I didn't multiply this whole thing by 0.1 for dt, if we go back to just 1, let's see what happens. It's pretty neat too. It's quite fast. I kind of like the slow motion that happened with dt equals to 0.1, so that's what I'm going to do. And then now, what if we display colors with the arrows? Actually, let's comment out the arrows. Oh, we also want to actually put in no stroke for this one. Ta-da! All right, I'm gonna let it run a little bit so you can see. Looks really nice. And you can make the grid even smaller to make it less granular. You can change the colors and you can also change the starting value, right? As you can see here, it's the outer part that is more chaotic and then it just kind of like come into the middle. But what if we actually change this to actually 0 to 2 pi? Actually, it gives a pretty neat effect too. I'll show you. Should we try a smaller size? I think so, but I hope that it doesn't crash my computer. I'm gonna save first, and then I'm gonna run. Wow, look at that. So beautiful. It looks like a flower that slowly emerges from this chaotic world of double pendulums. Wow, how neat is that? I really love this one. It's so beautiful and it's so simple too, right? We just really follow the basic rules of how to calculate the motion of the double pendulums, and it creates this beautiful visualization. So I hope that you enjoyed this one. Give it a try different variables, changing them, and see what kind of interesting things that emerge from your experiment. So give this one a try.